Start with bitwise operators, which are essential tools in embedded programming. Bitwise operators work directly on the individual bits of integers, making them incredibly efficient for tasks like memory management, hardware register manipulation, and flag handling. In embedded systems, where resources are often limited, using bitwise operations can help you write code that is both fast and memory efficient. For example, you might use bitwise AND, or XOR to set, clear, or toggle specific bits in a hardware register. This is especially useful when you need to control hardware at a low level or implement custom protocols. Mastering bitwise operators is a must for any embedded developer. Fields and C structures allow you to specify the exact number of bits used for each member. This is especially valuable in embedded systems, where every byte counts. By defining bit fields, you can efficiently map structure members to hardware registers or communication protocol fields, saving memory and making your code more readable. For example, you might define a structure with several 1-bit flags and a few reserved bits, all packed into a single byte. This approach is commonly used for status registers or configuration settings in embedded devices. Understanding bit fields helps you write compact, efficient code that interacts seamlessly with hardware. Const keyword in embedded C is used to declare constants, ensuring that certain variables remain unchanged throughout the program. This is particularly important in embedded systems for defining read-only data, such as lookup tables or configuration parameters. By marking data as const, you can prevent accidental modifications and enable the compiler to optimize memory usage, sometimes placing these constants in ROM. This not only protects critical data but can also improve performance and reliability, especially in systems where memory is at a premium. Using const correctly is a best practice for robust embedded software. Inline functions are a powerful feature in embedded systems programming. When you declare a function as inline, the compiler attempts to expand the function's code at each call site, reducing the overhead of function calls. This is especially useful for small, frequently called functions where performance is critical, such as those used in interrupt service routines or timing-sensitive code. However, it's important to use inline functions judiciously, as excessive inlining can increase code size, which is a concern in memory-constrained embedded systems. Balancing performance and code size is key when deciding to use inline functions. Circular buffers, also known as ring buffers, are fixed-size data structures that wrap around when full. They are widely used in embedded systems for implementing FIFO queues, buffering data between interrupt service routines in main code, and managing data flow and communication protocols. The implementation typically involves a buffer array and 2 pointers for reading and writing, using modulo arithmetic to wrap around. Circular buffers help ensure smooth data flow and efficient memory usage, making them ideal for real-time data processing and communication tasks in embedded applications. Understanding the difference between microcontrollers and microprocessors is fundamental in embedded systems. A microcontroller is an integrated chip that includes a CPU, memory, and peripherals, all designed for embedded applications. It's optimized for low power consumption and is often used in dedicated tasks. In contrast, a microprocessor is just the CPU and requires external components for memory and peripheral. Microprocessors are more powerful but consume more energy and are used in general-purpose computing. Knowing which to use depends on your application's requirements for power, integration, and performance. Harvard and von Neumann architectures are two fundamental designs in computing. Harvard architecture uses separate memory for instructions and data, allowing simultaneous access and improving performance, which is why it's common in microcontrollers. Von Neumann architecture, on the other hand, uses a single memory for both instructions and data, leading to simpler design but potential bottlenecks. This architecture is more common in general-purpose computers. Understanding these differences helps you choose the right architecture for your embedded application, balancing complexity, speed, and resource usage. Microcontrollers use several types of memory, each serving a specific purpose. Flash memory is non-volatile and stores the main program code. EEPROM is also non-volatile and is used for storing small amounts of data that must persist across power cycles. SRAM is volatile and provides fast, temporary storage for variables and stack operations. ROM is often used for bootloaders or firmware that doesn't change. Understanding these memory types helps you design efficient, reliable embedded systems that make the best use of available resources. Memory-mapped I/O is a technique where peripheral devices are assigned specific memory addresses, allowing them to be accessed using the same instructions as regular memory. This simplifies hardware interfacing and enables powerful memory manipulation operations. By treating peripheral registers as memory locations, embedded developers can write cleaner, more efficient code for controlling hardware. Memory-mapped I/O is a cornerstone of embedded system design, making it easier to interact with sensors, actuators, and other devices. Watchdog Timer is a hardware feature that helps maintain system reliability. It works by resetting the system if the software fails to feed it regularly, which can happen if the program hangs or enters an infinite loop. In embedded systems, watchdog timers are crucial for recovering from unexpected errors and ensuring the system remains responsive, even in harsh environments. Proper use of a watchdog timer can be the difference between a robust, reliable product and one that fails unpredictably. Static memory allocation reserves memory at compile time, making it predictable and efficient. In embedded systems, it's commonly used for global variables, constant data, and fixed-size buffers. The main advantage is that memory usage is known ahead of time, avoiding fragmentation and runtime allocation overhead. However, static allocation lacks flexibility, as the memory size cannot be changed during execution. Choosing static allocation is often a trade-off between predictability and adaptability, especially in resource-constrained environments. Dynamic memory allocation allows memory to be reserved at runtime using functions like malloc and free. While this offers flexibility, it introduces challenges in embedded systems such as limited memory resources, potential for fragmentation, and unpredictable execution times. These issues can affect system reliability, especially in long-running or real-time applications. Careful management and, when possible, minimizing dynamic allocation are key strategies for robust embedded software. Stack overflow occurs when the stack exceeds its allocated space, potentially causing system crashes or unpredictable behavior. In embedded systems, preventing stack overflow involves limiting recursion, minimizing local variable usage, and using static allocation for large buffers. Implementing stack monitoring and sizing the stack based on worst-case scenarios are also important. By proactively managing stack usage, you can avoid hard-to-diagnose bugs and ensure system stability. Memory fragmentation happens when free memory is split into small non-contiguous blocks, making it difficult to allocate large chunks of memory. In embedded systems, this can lead to inefficient memory usage and even system failures if critical allocations can't be made. Avoiding fragmentation often means favoring static or pooled memory allocation and minimizing dynamic allocation. Understanding and managing fragmentation is key to building reliable, long-running embedded applications. Memory leak occurs when dynamically allocated memory is not properly freed, leading to gradual depletion of available memory. In embedded systems, this can be catastrophic, especially in devices that run for long periods. Detecting leaks involves using memory profiling tools, tracking allocations, and performing periodic checks. Prevention strategies include careful management of dynamic allocations, using static allocation when possible, and thorough code review. Addressing memory leaks is essential for system reliability. Interrupts are signals that cause the processor to pause its current execution and handle a higher priority task. They are vital in embedded systems for responding quickly to external events, managing efficient I/O, and implementing real-time features. Interrupts also play a key role in power management, such as waking the system from sleep. Mastering interrupt handling is fundamental for building responsive and efficient embedded applications. Interrupts can be classified as maskable or non-maskable. Maskable interrupts can be disabled by software and are typically used for peripherals and timers, allowing prioritization of tasks. Non-maskable interrupts, NMIs, cannot be disabled and are reserved for critical events like power failures. NMIs always have the highest priority and must be handled immediately. Understanding the distinction helps you design systems that respond appropriately to both routine and emergency events. Interrupt latency is the time between an interrupt request and the start of the interrupt service routine ISR. In real-time systems, low and predictable latency is crucial for meeting deadlines and ensuring system responsiveness. Factors affecting latency include processor speed, interrupt priority, and the current state of the processor. Optimizing for low latency is a key consideration in the design of real-time embedded systems. Writing efficient interrupt service routines, ISRs, is essential for system performance. ISRs should be kept short and fast, avoiding blocking operations and minimizing dynamic memory allocation. Use the volatile keyword for shared variables and disable interrupts only when necessary. For longer tasks, consider using a flag and poll mechanism. Properly saving and restoring context ensures reliable operation. Following these best practices helps maintain system stability and responsiveness. Interrupt nesting allows higher priority interrupts to interrupt lower priority ISRs. This is useful in systems with multiple interrupt priorities, ensuring that critical events are handled promptly. However, interrupt nesting increases system complexity and can lead to stack overflow if not managed carefully. It's typically used in complex real-time systems with strict timing requirements, where responsiveness to critical events is paramount. Real-time operating system, RTOS, is designed for deterministic time-critical operations, providing predictable task scheduling and supporting priority-based preemptive multitasking. In contrast, a general-purpose OS focuses on overall performance and user experience, often using time-slice scheduling and offering more features. RTOSs are essential for embedded systems that require guaranteed response times, while general-purpose OSs are better suited for applications where flexibility and features are more important than strict timing. Task priorities in an RTOS determine the order in which tasks are executed. Higher priority tasks preempt lower priority ones, ensuring that time-critical operations are handled predictably. Proper assignment of task priorities is crucial for efficient resource allocation and meeting real-time requirements. Mismanagement can lead to missed deadlines or inefficient system behavior, so understanding and configuring task priorities is a core skill for embedded developers working with RTOSs. Priority inversion occurs when a high-priority task is indirectly preempted by a lower-priority task, often due to resource contention. This can lead to missed deadlines in real-time systems. Mitigation strategies include priority inheritance, where the lower-priority task temporarily inherits a higher priority, and priority ceiling protocols. Careful design of task interactions and resource sharing is essential to prevent priority inversion and ensure system reliability. Preemptive multitasking allows the operating system to interrupt tasks at any time, ensuring high-priority tasks get immediate attention. This approach is more complex but provides better real-time performance. Cooperative multitasking, on the other hand, relies on tasks voluntarily yielding control, which is simpler but can lead to poor responsiveness if tasks don't yield regularly. Most RTOS implementations use preemptive multitasking to meet real-time requirements. Semaphores are synchronization primitives used in RTOS-based systems to control access to shared resources and synchronize tasks. Binary semaphores are used for mutual exclusion, while counting semaphores manage multiple resources. Proper use of semaphores is crucial for preventing race conditions and deadlocks, ensuring that multitasking systems operate smoothly and reliably. Serial communication can be synchronous or asynchronous. Synchronous communication uses a clock signal to synchronize data transfer, offering higher speed and efficiency but requiring extra wiring. Asynchronous communication like UART doesn't use a shared clock and relies on start-stop bits, making it simpler and more common in embedded systems. Each method has its advantages, and the choice depends on application requirements for speed, complexity, and wiring. SPI, or Serial Peripheral Interface, is a synchronous serial communication protocol known for its high speed and simplicity. It supports full duplex communication and can connect multiple slave devices using 4 lines: MOSI, MISO, SCK, and SS. SPI is widely used in embedded systems for efficient data transfer between microcontrollers and peripherals, making it a go-to choice for high-performance application. I2C, or Inter-Integrated Circuit, is a serial communication protocol featuring a 2-wire interface, SDA and SCL. It supports multiple masters and slaves on the same bus, with built-in addressing and moderate speed. I2C is commonly used for communication between microcontrollers and sensors or other peripherals, offering a balance between simplicity, flexibility, and performance in embedded systems. CAN, or Controller Area Network, is a robust message-based protocol designed for automotive and industrial applications. It supports multi-master communication, built-in error detection, and priority-based message arbitration. CAN is known for its high noise immunity and real-time capabilities, making it ideal for distributed control systems in harsh environments. UART, or Universal Asynchronous Receiver Transmitter, is a simple and widely supported serial communication protocol. It uses 2 wires TX and RX and doesn't require a clock signal, relying on start and stop bits for synchronization. UART is typically used for point-to-point communication, debugging, and interfacing with sensors in embedded systems. Its simplicity and flexibility make it a staple in embedded design. In-Circuit Emulator, ICE is a hardware tool that emulates the behavior of a target microcontroller, enabling real-time debugging. ICEs allow developers to monitor internal registers, set breakpoints, and analyze performance. They provide deep insights into hardware-software interactions, though they can be expensive and may not perfectly match the timing of the final system. ICEs are invaluable for complex embedded development and troubleshooting. JTAG, or Joint Test Action Group, is a standard interface for on-chip debugging and programming. It provides access to debug modules, allows control of processor execution, and supports boundary scan testing. JTAG is widely used for programming flash memory and debugging embedded systems, offering a standardized way to interact with chips from different manufacturers. Logic Analyzer is a test instrument that captures and displays multiple digital signals, making it invaluable for analyzing communication protocols and debugging timing issues. Logic analyzers help developers correlate events across signals and optimize system performance. They are especially useful in complex embedded systems where understanding the timing and interaction of multiple signals is critical. Debugging embedded software requires a variety of techniques, including print debugging, LED indicators, assertion statements, watchpoints, breakpoints, single-stepping, and memory dumps. Using IDE-based debugging tools can also be highly effective. The choice of technique depends on available resources and the specific problem. Mastering these methods is essential for efficiently identifying and resolving issues in embedded systems. Boundary value analysis is a testing technique that focuses on the edges of input ranges, where many bugs tend to occur. In embedded systems, testing at minimum, maximum, and just above or below these values helps ensure robust error handling and system reliability. This approach is crucial for catching issues related to data type limits, overflow, and extreme operating conditions. Testing involves testing individual components or functions in isolation. In embedded systems, this can be achieved by creating test harnesses, using mock objects, and adopting test-driven development practices. Automated unit testing frameworks like Unity or CPP UTest can streamline the process. Unit testing helps catch bugs early and ensures that each part of the system works as intended before integration. Code coverage measures how much of your source code is executed during testing. It's a valuable metric for identifying untested code, dead code, and unreachable branches. While 100% coverage doesn't guarantee bug-free software, it helps guide the development of additional test cases and improves overall test quality. Monitoring code coverage is an important part of embedded software testing. Fuzzing is a testing technique that involves providing invalid, unexpected, or random data as input to a system. In embedded systems, fuzzing can uncover vulnerabilities, improve error handling, and increase robustness by simulating faulty sensor readings or injecting noise into communication channels. It's a powerful tool for finding edge cases and ensuring your system can handle unexpected inputs gracefully. Inline assembly allows you to embed assembly language instructions directly within C code. This is useful for accessing hardware-specific features, optimizing performance-critical sections, or achieving precise timing. For example, you might use inline assembly to insert a no-operation instruction or to interact with special hardware registers. While powerful, inline assembly should be used sparingly to maintain code portability and readability. Loop unrolling is an optimization technique where the body of a loop is replicated multiple times to reduce loop overhead and improve instruction pipelining. In embedded systems, this can lead to faster execution and better use of processor resources. However, it also increases code size, so it's important to balance the benefits against the available memory, especially in resource-constrained environments. Function inlining replaces a function call with the actual body of the function, reducing call overhead and potentially improving performance. It's best used for small, frequently called functions where timing is critical. However, excessive inlining can increase code size, so it's important to use this technique judiciously, especially in embedded systems with limited memory. Lookup tables store pre-computed results for complex calculations, allowing embedded systems to speed up operations and reduce CPU load. They're often used for implementing nonlinear functions or frequently performed calculations. While lookup tables can significantly improve performance, they consume additional memory, so it's important to weigh the trade-offs based on your application's needs. Volatile keyword tells the compiler that a variable's value can change unexpectedly, such as when modified by hardware or interrupts. This prevents the compiler from optimizing away necessary reads or writes, ensuring the most up-to-date value is always accessed. Using volatile correctly is crucial for proper operation in multi-threaded or interrupt-driven embedded systems. Bootloader is a small program that runs before the main application in an embedded system. Its main roles include initializing hardware, loading the main application into memory, performing system checks, and facilitating firmware updates. Bootloaders are essential for systems that require field updates or recovery mechanisms, enhancing reliability and flexibility. Watchdog timers are hardware timers that reset the system if not regularly fed by software. They are crucial for recovering from software hangs, detecting unexpected errors, and ensuring system reliability in harsh or unstable environments. Proper use of watchdog timers is a key practice in developing robust embedded systems, especially those with safety requirements.